Welcome, folks. Talking about advanced applications of integrals today and just an introduction to a little bit of modeling with differential equations. This is going to give us the foundation to be able to discuss two different types of differential equations, namely separable first-order differential equations and linear first-order differential equations that are additional applications of integrals. So first, tell you what a differential equation is. We'll talk about what it means to be a solution of a differential equation, and then we'll talk about solving initial value problems. So a differential equation is an equation, obviously, involving one or more derivatives of some unknown function. Now, the goal in studying a differential equation usually is to find that unknown function, or at least find out as much as you can about it. So we'll talk about this a little more in the next couple of videos, but in general, we would like to find an explicit representation for that unknown function. Now, a few things. Oftentimes, the unknown function can be a little bit difficult to spot. So one key to spotting the unknown function is to look for a derivative. A derivative tells us what the unknown function is. In addition, oftentimes the independent variable in these differential equations is implied. So we'll see what we mean by that also. And finally, the order of a differential equation is known as the highest derivative you see in the equation. But for our purposes, we're going to focus on first order differential equations. So the highest order derivative we'll see is a first derivative. Okay, so we'll go ahead and just drive a few differential equations here with some descriptions of a model. So let's suppose that the rate of change of a population is proportional to the population size. Okay, so there are a few keywords here that will give us a differential equation. The first thing we'll do is identify the population size at time t as capital P of t. Now, when we say rate of change of the population, rate of change means the same thing it did in Calculus 1, which is a derivative. So rate of change of the population is P prime of t, and when we say proportional to, we mean equal to a constant times that thing. A perfectly good differential equation, therefore, is P prime of t equals R times P of t. Now, this could come in a couple other forms. So those couple other forms are either dp dt equals R times P, or maybe P prime equals R times P. Now, we see in both of these that the derivative is on the P. That tells us that P is the unknown function. Okay, and finally, this second version where we write P prime equals R times P is what we mean when we say that the independent variable is implied. So it's sort of common, it's common to drop that of t explicit dependence and just write P prime and let it be understood that it's a function of time. Okay, let's do another one. Let's talk about radioactive decay. Suppose that the rate of change of the amount of a radioactive substance is proportional to the amount of that substance. So a lot of similar things here. We'll see one difference in this equation with the last one. Okay, so similarly, we see that if x is the amount of radioactive substance, that the rate of change of that amount is x prime. We know that proportional to means a constant times that quantity. And one sort of slight difference here, we have a decay process, which means that the amount of stuff is decreasing. Of course, we know if something is decreasing, its derivative should be negative, right? So we'll take dx dt equal to minus rx, or maybe x prime equals minus rx. Okay, and again here, the unknown function is x of t. Okay, here's one more example. Let's suppose that the rate of change of the temperature of an object is proportional to the difference between the temperature of the object and the ambient temperature. We'll drive a differential equation model for this too. So in this case, we take U of t to be the temperature of the object. T sub a, which is a constant, is going to be the ambient temperature. And similarly to the last two examples, we have a couple of things here. We have the rate of change of the temperature U. So again, that's U prime of T. And the difference between the temperature of the object and the ambient temperature we can write as T sub A minus U. So here's a perfectly good differential equation model for this so-called Newton's law of cooling. We'll take it to be du dt equals R times T sub A minus U, or U prime equals R times T sub A minus U. Now, a good thing to do here is to give this model a little sniff test to make sure that it does the right thing. In this example, I like to compare it to maybe a hot cup of coffee sitting in a cool room. If we have a hot cup of coffee in a cool room, we know that the temperature of the coffee is greater than the temperature of the room. That tells us that the difference, T sub A minus U, is negative. And if T sub A minus U is negative, U prime is also negative, which tells us that U is decreasing. And that's what we expect to happen, right? If we have a hot cup of coffee in a cold room, we'd expect the temperature of that coffee to decrease over time. So the derivative should be negative. That's always a good check to give your differential equation to make sure it acts like you would expect it to act in some of those simple situations. Okay, sort of a summary of those three models. And again, here we see the implicit or the unknown function having dependence on the independent variable implied, right? So in this first model, P of t is the unknown function. In the second model, x of t is the unknown function. And with my formatting a little bit off here, sorry about that, u of t is the unknown function in this example. Okay, so a little bit of modeling with differential equations. Okay, so let's talk about how we talk about a solution of a differential equation. We've talked about how a differential equation is an equation involving one or more derivatives of some unknown function. A function is the solution of the differential equation if, when we substitute it into the differential equation, it makes the equation true. So this is something that we're used to doing with algebraic equations all the time. Let me give a quick example here. For the algebraic equation, for instance, x squared minus 4 equals 0, we know that minus 2 is the solution. When you plug in minus 2 to this equation, we know that we get minus 2 quantity squared minus 4, which is 4 minus 4, which is 0. Check. On the other hand, it's also quick to see that 3 is not a solution. When we substitute x equals 3, it doesn't make the equation true. So we know that 3 is not a solution of the algebraic equation. So same idea with differential equations. Substitute a function in and see if it makes the equation true. Here's an example. Let's go ahead and show that u of t equals e to the 7t is the solution of this differential equation, dy dt minus 7y equals 0. Okay, in order to do this, we'll need to compute, and I should have probably written here y of t, not u of t. In any case, we'll need to compute both dy dt and 7y. Now, we know how to take derivatives of these functions since we know how to take derivatives of exponential functions. Since dy dt is 7e to the 7t, we can see that dy dt minus 7y is just dy dt, is just 7e to the 7t minus 7e to the 7t, which is 0, making the equation true. Hence, e to the 7t is the solution of this differential equation. Here's another one. Let's find values of r such that cosine of rx is the solution of this differential equation. Here we have a second order equation. In general, we're not dealing with second order equations, but it'll still illustrate the point of plugging things in. Okay, so in order to plug in y of x to this differential equation, we need the second derivative. So here we see the original function. Of course, to get the second derivative, you need the first derivative, which the second derivative turns out to be minus a times r times cosine of rx. Plugging in, we see that the equation simplifies, and it turns out we can choose an r to make this equation true. Here we see that when substituted into the differential equation, y double prime plus 9y is equal to, simplifying, a times the quantity minus r squared plus 9 times the cosine of rx. So if we want this to be equal to 0, we better have a times minus r squared plus 9 times cosine x equal to 0. Now, of course, we can choose r to make this 0 as long as r is 3 or minus 3. So our function cosine of rx is a solution if r is 3 or minus 3. Of course, that sort of yields the same function since cosine is even. In any case, it turns out that this is independent of the constant value a. So you can choose the constant value a to be anything you want and get the same idea. Okay, let's talk about initial value problems. A differential equation together with a well-formed, and we'll talk about that just briefly. Initial value is called an initial value problem. So you have to have two things to be an initial value problem. You have to have a differential equation and an initial value. Now, a function is a solution of an initial value problem if it's a solution of the differential equation and it satisfies the initial value problem. So to check or to verify whether a function is a solution of an initial value problem, there are two things we have to look at. We have to ensure that our function is a solution of the differential equation, which we just talked about that. And then we should also make sure that it satisfies the initial value. And we'll see how to do that in a second. Okay, here's an example. Let's show that this function, 2/3 e to the minus 2x plus 1/3 e to the x, is the solution of this initial value problem. So again, here is a differential equation together with an initial value. We better be true. It better be the case that when we plug in 0, we get 1. Okay, so let's check the differential equation first. So with function 2/3 e to the minus 2x plus 1/3 e to the x, we see that the derivative is minus 4/3 e to the minus 2x plus 1/3 e to the x. Well, we can substitute that quantity in, right? Here is the first derivative, and here is 2 times the original function. Simplify, simplify, simplify. You can see that there are two types of terms here. There's an exponential term with an e to the minus 2x and an exponential term with an e to the positive x. I have a slight typo here, so I'll fix that in just a second. So when we simplify, we see that we have e to the minus 2x times minus 4/3 plus 2 times 2/3. Of course, that part is 0. And we have e to the x times 1/3 plus 2 times 2/3, which is just 1. So we end up with e to the x, and our function satisfies, or is a solution of the differential equation. Now, to see it satisfies the initial value, sort of a similar procedure. So we see that when we substitute x equals 0 into our function, we get out 2/3 e to the minus 2x plus 1/3 e to the x at 0. Of course, 2/3 plus 1/3 is just 1, and our function satisfies the initial value also. So this function is a solution of the initial value problem. Okay, let's see one more example here. Let's have a look at the function u of t equals 70 plus c times e to the minus 3t. And let's show first that it's a solution of the differential equation. And then let's determine c such that u of 0 equals 100. So with u equal to 70 plus some constant times e to the minus 3t, we see that the derivative is minus 3 times a constant times e to the minus 3t. And we can substitute that expression in to our differential equation. Here's the derivative, and 3 times the function itself. Simplify, simplify, simplify. We see that multiplying the exponential term is negative 3c plus 3c, which reduces to 0, and we end up with 210 as we expect. Okay, so our function is a solution for any value c. In order to determine c such that u of 0 is 100, we'll just go ahead and plug in 0 and pick the c that works. We can see that u of 0 is 70 plus c times e to the minus 3t evaluated at t equals 0. Of course, e to the 0 is just 1, and we end up with 70 plus c here. Now, if we want that to equal 100, it's quick to see that c has to be 30. So here's that computation. C has to be 30. So we can see that when c is equal to 30, the solution of our initial value problem is u of t equals 70 plus 30 e to the minus 3t. This procedure is sort of a common procedure when it comes to differential equations. We'll often see that we'd like to solve for some constant that actually comes from that constant of integration in order to find the solution of an initial value problem. Okay, folks, hope you've enjoyed this video on modeling with differential equations, what it means to be the solution of a differential equation, and what it means to be a solution of an initial value problem. Have a great day, and we'll see you next time. Bye-bye.